So I'm glad there's still some people left. So my name is Daniel. I'm at the Nanoportfolios group at INRS. My supervisor is Andreas Rüdiger. He's not here today. And to begin, we are basically just an experimental group. I'm basically the one-man simulation group. So this is a side project which began during my time in Germany, during my master's studies, and which is still work in progress. So the topic is strain-induced enhancement of surface self-diffusion on strontium titanate surfaces. So I will answer the most important question at the beginning: why should even anyone care about? Because we see an AFM image. This was done by a former colleague, and we see atomically flat surfaces with a width of 1 micrometer. And 1 micrometer doesn't sound much, but this is 10 times larger than other groups are able to produce such structures. And these structures can be used as a substrate, for example, for self-assembling polymers, whatever. And we found a model which can answer why we get these massive atomically flat surfaces. And the more important part is the underlying mechanism is like a universal concept for every surface, independently of the material. First of all, I want to give an overview. First, I introduce like the material, why is strontium titanate even interesting, my objectives, a quick overlook about the simulation setup, and the result for unstrained and strained strontium titanate, followed by conclusion and outlook. First of all, strontium titanate has 2 different phases, but for my talk, only like the room temperature cubic phase is relevant. We have like very interesting properties. The lattice constant I only show you because it will be important in a few minutes. It's 3.9 angstrom. We have the direct and indirect band gap over 3 eV, so the material is transparent as a consequence. We have like a high relative permittivity, so it's also interesting for capacitors. We like, it's a superconductor actually under certain conditions, so 300 millikelvin, which is a very large research topic on its own. Photocatalytic properties like water splitting are very popular topic. And for us in our group, actually the surface engineering is the interesting part. Because due to the different layers, strontium titanate and titanium dioxide, we can produce surfaces with 2 different terminations: strontium oxide, titanium dioxide. For the most part, titanium dioxide is preferred because strontium oxide reacts with CO2 of the ambient air, creates carbonate, and just destroys the termination. So it's not atomically flat anymore. All these unique properties lead to different applications, ranging from capacitors over water splitting into optical setups and to substrates. We are basically want to use strontium titanate as a substrate. And first of all, why is strontium titanate even a good substrate? So I have like 2 main points of what a good substrate is. There are of course many other points, but the 2 most important: it should be atomically flat, and it should be chemically pure, so there are no surprises. And 10 years ago, a former colleague was able to produce defect-free atomically flat titanium dioxide terminated strontium titanate surfaces. And this was actually very special because beforehand the people used HF, and as a result we get fluoride doping in our strontium titanate surfaces, and so it's not defect-free. So really, through this hydrothermal polymer hydrothermal process activated by microwave radiation, we were able to produce defect-free surfaces, which are because they have titanium dioxide terminated, even stable under ambient conditions. So there's no need for a vacuum or protected atmospheres. So, and all the surfaces I showed you are not actually plane surfaces, but these are terrace structures. Terrace structures, as the name says, are terraces. They have a certain width and a certain step height. And all these terraces are on its own atomically flat. They are typically arranged in 100 to 200 nanometers. They are titanium dioxide terminated, and the the reason why we have terrace structures and not like a plain surface is the called misfit angle. Because if you produce a substrate, the two planes, the bottom and the top plane, are not perfectly perpendicular. You always have a small misfit angle. And this is due to technical limitations. There's nothing we can do about it. It's in the range of 0.13. The smaller the misfit angle, the larger are the terraces. So we want to keep it small. But since this misfit angle is determined by different techniques, we still want to increase the terrace width without changing the misfit angle. And this can be done by self-diffusion. If you just, for example, with thermal annealing, we activate the atoms to diffuse. And so without changing the misfit angle, we can now, for example, double, quadruple, whatever the terrace width. But the step height will also increase at the same time. And this is now the AFM scan of the image I showed you on my first slide. We achieved like 1 micrometer wide steps, which are close to be atomically flat. So, and now the question is, what did we do differently from other groups? We achieved 1 micrometer, all the others 100, 200. And we didn't use like a strontium titanate substrate. We first used a thermally annealed magnesium oxide substrate. And then we deposited the magnesium sputtering the strontium titanate on the magnesium oxide. And both materials are cubic, but they have different lattice constants, like NGO 4.2, strontium titanate 3.9. And we get a massive lattice mismatch of 7.9%. This would be in bulk completely impossible. But since we have thin films, this is possible. And there is experimental evidence for silver that strain has an impact on the diffusion barrier. So let's go to the objectives. So first of all, we have our experimental observation. And now we thought about like investigating numerically. And since the thermal annealing process of these terrace structures is in the range of like 1 hour, we need a simulation method which is capable of simulating 1 hour. So our choice is the kinetic indicator simulation. But there's basically no work done on the strontium titanate surface diffusion. So we could run a KMC without any knowledge, but this would result in many other assumptions and in a very inaccurate way. So what we want to do is obtain a diffusion model with the help of density functional theory, so obtaining the diffusion barriers, etc. So the objective for this talk is developing a diffusion model for the surface diffusion for strained and unstrained strontium titanate. So for unstrained, because just to have a reference, what is actually diffusing, and then for the strained one, how the strain affected. So just a quick overlook of the simulation. We use a 3x3 supercell. We constrain the bottom 2 atomic layers and use like a vacuum 3 times the lattice constant, so around 12 angstrom. And normally we would like conduct a net calculation, for example, to obtain the perfect diffusion path, diffusion barrier. But since we want to give our KMC model the largest amount of freedom possible, so maybe at higher temperatures also secondary diffusion paths have significant impact, we actually sampled our surface. And on every grid point you see, it's sampled with 13 by 13 points. We use surface pieces which properly diffuse oxygen, strontium, strontium oxide, titanium, titanium dioxide, and just move each species over the surface and fully relax the structure. So as a result, we get like diffusion energy maps, which can be used in the KMC model in the future. For example, this is for the titanium atom. And we see like the dark color is like small energy barriers and the white colors are high energy barriers. So for example, for the titanium would sit in its equilibrium position on the strontium side and diffuse via the oxygen atom to the other strontium side. And this was done for all 6 surface species. To wrap the results up, I expect the diffusion barrier for the most optimal diffusion path. And what we see is for oxygen and O2, oxygen, a single oxygen atom has a higher diffusion barrier, which is not surprising because it wants to likely form O2 on the surface, where O2 is like chemical stable, so doesn't want to react. Strontium oxide are very similar because strontium has like the lowest diffusion barrier and doesn't, the lowest electron negativity and doesn't want to react with the surface. Titanium and titanium dioxide, titanium is known to be very reactive, so it's very likely that it's one immediately to form titanium oxide or dioxide. But in general, the rate limiting steps are basically strontium oxide and titanium dioxide, since it's unlikely under ambient conditions that titanium will diffuse on its own without oxidizing. So after we obtained like the unstrained diffusion model, we go to the interesting part and the results of strain strontium titanate. We didn't obtain maps because like under high strain, it's very difficult to actually calculate to converge EFT model. So we first introduced only titanium editors because titanium had the largest energy barrier. So if it's true for titanium, we should see the same effect for the other species as well. So we defined 3 positions: 0, which was the equilibrium position, 27, which is on top of another titanium atom, and 6, which is on top of the oxygen atom. And what we see, the strain, positive strain is tensile strain, and negative is the compressive strain. And what we see in the gray marked area between -6 and +1 is that we have like this quadratic area, which indicates like the elastic response of the system. So there are 2 main points. First of all, it's quadratic, so it's indicates elastic behavior, and it's not centered at 1, 0. Why is the curve not centered at 1, 0? Because oxides are much more stable under compression than they are under tensile stress. So and we see for the higher the strain, the higher the diffusion coefficient, at least in the elastic regime, because in plastic it gets unpredictable. And since this is just based on binding energies that we compress or move away the atoms, the binding energy drops, and therefore also the binding energy of the surface species in this. And now we come to the end. After we see in elastic regimes, we have a nice curve. What is actually happening in the plastic regime where we get the unpredictable spiking? There's a nice graphic. On the bottom, we have like this MgO substrate, and the first strontium titanate cells are able to stretch themselves to fit on the 4.2 angstrom. But at some point, when there are too many layers, the stored elastic energy is so high that it's easier for the system to create dislocations and start relaxing. What can also happen is like strain-induced local phase transition. So maybe the octahedra in the strontium titanate starts tilting, rotating, whatever. And at the end, in the zone 3, it's fully relaxed again. This happens in the ballpark of like 20 to 30 nanometers for strontium titanate. So after that, we have a fully relaxed structure. So to come to an end, we obtain a surface self-diffusion model for unstrained strontium titanate. Just for reference, O2 has the lowest diffusion barrier and titanium the highest. And we showed that with strain drastically reduces the diffusion barrier. So for small misfits, it's depending on the material, the system remains in the elastic regime to get a nice quadratic curve. For titanium, the diffusion barrier drops below 1 electron volt. And if we remember the Arrhenius equation, it's an exponent of the E function. And so we get a massive increase of the diffusion. And the most important part of this, basically the key message of this talk, is that the reduction of diffusion barriers under strain is a universal feature, because there's nothing in the model which restricted to only to strontium titanate. It was, of course, only simulated for strontium titanate, but it was experimentally shown for silver as well, which are completely other material, and it's just based on reduction of binding energies due to strain. For our outlook, we of course want to more detailed simulations for surface diffusion and strain. So maybe we get another DFT code which is able to calculate more easily strained geometries. Maybe even obtaining a simplified model for strain-dependent diffusion barriers. So if there are many species who show this quadratic curve, so maybe we can this use as an approximation for every species. And of course, set up of the kinetic Monte Carlo simulation once all the simulation work is done. At the end, I want to thank the nanophotonics team and my colleagues from the University of Applied Science, Stony Brook University, and thank the Leibniz Supercomputing Center for the collaboration.
And the curls, this is a slab model you have showed on which there is a grid and added quantity. So in the small slab model, you cannot possibly have a plus diffusion, right? So it doesn't this jumps just the vicissitudes of how the grid falls, and the grid points fall out as you stretch.
I mean, yes, you're correct. For like very large plastic deformation to see the effects, we need a much larger model. But our data of the atomic coordinates shows that at some points the atomic coordinates don't follow a linear curve anymore. So if we strain the system for like 1%, we should see each atomic coordinate move 1%. But at some point, at some stress, we see it's not linear anymore, but it starts jumping. So some atoms move much more than others.
So you do see this integration of the original.
Yes.
And a related question: what does the stresses corresponding to some strengths? To a strain corresponds a stress, right? So do a strain of 10% experimentally, possibly 7-9%. What are the stresses corresponding to such? What stresses are generated by inducing such a strain? And are those realistic stresses?
I don't have any stress values.
And it involves the DFT points, right?
Yeah, but since we are more interested on the experimental side, so we just basically look on the lattice mismatch of substrates. So we are not that interested on the specific stress values, because we see from our experimental setups when we deposit on the substrate that the film is stable, so it's not delaminating.
That the experimental unequivocally shows that the interface is coherent. That's such a
yes. For various thin films, we see a stable film. So
stable is stable. Coherent. The coherent interface, that's 7.9%.
Our XFT data shows that it's a fully crystalline sample. So therefore, it's.
So with the questions there. It was a very nice presentation. I would like to ask you a few things about your model. I don't see any vacancies in your migration mechanism. Now, strontium titanate should have anionic vacancies, oxide ion vacancies, should have cationic vacancies. And vacancies would enhance migration of species. But your model does not include vacancies around the surface vibration.
No, we didn't, since we are based on the fact that we are able to produce defect-free surfaces, and so we just
Yeah,
assume
but you have auto formation. Now, if you do have auto formation, you are leaving vacancies, oxygen vacancies there. And in addition, they are in equilibrium with your oxygen partial pressure. So the oxygen atmosphere controls the vacancy concentration on the surface. And those are highly defective surfaces. By highly defective, I mean oxide ion, they can have oxide ion deficiency or different oxide ion population. Now, this will control also your cation population on the surface. And my second question is, in the model, did you include also subsurface exchange of species? For example, strontium migrating to the surface, titanium dipping into the surface. The driving force for it would be titanium would be having a great driving force for the building of the federal ordination. So dipping deep to the under the surface will be a driving force for titanium. The other than strontium will have no such driving force, so it will be easily. So you have different gradient of both the tions. So you have, in other words, you have strontium segregation on those surfaces.
no, first of all, for the oxygens, it's produced under oxygen flow. We assume no oxygen vacancies, at least not that significant amount. And the other thing is, like, we deposit it at a really high temperature. So during the deposition, the material already can go to this crystalline state. So we assume that's basically, since it's still work in progress, we assume that during the time, the atoms basically are deposited on a plane surface. And
Okay, then allow me to go a bit further. Why are you so sure you have titanium dioxide? I know that there is a big plane that those terraces are titanium dioxide, but there is an equal plane that they are always strontium oxide there.
of course, we are able with thrust measurement to determine the surface termination.
With what measure?
Tip-enhanced Raman spectroscopy. There you are possible to really measure the surface termination.
How exactly do you difference between the strontium and titanium?
Because
it's a single atom layer.
Yes, I mean, we are basically at the moment we will publish a paper on this, and I don't work with the system. So it's basically a gold tip, which is activated with a red laser, and then with the near fields, you can measure atomically one atomic layer.
Okay.
This is
Okay.
Another question?
Can you explain like why the compression can also reduce the energy value? So I would imagine that if you have a highly compressed field, atoms are close together, it's much difficult to squeeze atom and find the distribution possible. I understand the like tensions, they are far away, but you need to move, but compressing them much closer. Difficult. Pretty well.
Everybody, all the atoms are so unhappy, okay? So that's why you have, I mean, when you're under compression, you're really raising the strain in so much that essentially the other atoms can move much more freely inside, because you already have a lot of, you're in a very unstable position. So that puts a lot of energy in the system. Typically, indeed, that lowers the diffusion barrier, but those are very highly strained.
Sure, man.
And this is at the surface. There's nothing involved. Sorry.
Thank you for your answer.
Okay, so I think we can thank our speaker and all of the transcripts.